Hello learners and welcome back to Fractal Frontier Math. If you are preparing for the CSIR NET, GATE or other competitive exam, this series on previous year questions on ordinary differential equation is going to be highly valuable for you. In our previous videos, we explored important concepts like Picard-Lindelof theorem of existence and uniqueness, Peano's existence theorem, and tackled several specific initial value problems. If you are new to this channel, you are advised to first watch previous videos where we have explored many aspects on existence and uniqueness of solutions of the initial value problems. This video is a continuation of our series on initial value problem. So check the playlist, it will help you a lot. Now we will use our previous discussion to answer CSIR NET December 2016 problem, which states that in initial value problem y dash t equal to fyt subject to y0 equal to a belongs to R, where f is a function given defined from R to R. Then we have to examine which option is true and which is not. So first option is there exists a continuous function and a belongs to R such that the above problem does not have a solution in any neighborhood of 0. Second option is the problem has a unique solution for every E belongs to R when f is Lipschitz continuous. Third is when f is twice continuously differentiable, the maximum interval of existence for the above initial value problem is R. The maximal interval of existence for the above problem is R when f is bounded and continuously differentiable. So this is Picard-Lindelof theorem, which states that if a function f of xy defined on a domain D is continuous with respect to x and Lipschitz continuous with respect to y, then the initial value problem dy by dx subject to the condition yx0 equal to y0 has a unique solution in an interval containing x0. And also the Peano's existence theorem, if the function is continuous in a neighborhood around the point x0, y0, then the initial value problem has at least one solution in some interval around x0. So by Picard-Lindelof theorem, we can guarantee that the solution is unique, and by Peano's theorem, we can just say that the initial value problem has at least one solution. It does not guarantee about the uniqueness. So we can summarize that if f is continuous with respect to x and Lipschitz is continuous with respect to y, then solution exists and is unique. And if f is continuous around x0, y0, then solution exists. So by using these two theorems, we will analyze the question. So the first option is if f is a continuous function from R to R, okay, then by Peano's existence theorem, this initial value problem has at least one solution around x0, but the option saying that the problem does not have a solution in any neighborhood of 0, which is not correct. So by Peano's existence theorem, there will exist a solution. So this option is not true. You can mark it. Okay. In second option, it is given that when f is Lipschitz continuous, then the problem has a unique solution for every a belongs to R. So by Picard-Lindelof theorem, if f is Lipschitz continuous, that means it will continuous as well as Lipschitz continuous, then it will have a unique solution. So option 2 is a correct option. For option C, we will provide a counter example because the option is saying that when f is twice continuously differentiable function, the maximum interval is R. So it is not necessary that maximum interval is R. Sometimes there may be some breakdown point alpha or some other points where solution tends to infinity. So it will not be the whole real number. So for this we will take an example. Consider the differential equation dy by dx equal to y square. Subject to the condition y0 equal to a, then its solution we can check that yx will be a upon 1 minus ax. So the condition is x will not be equal to 1 by a. So the maximal interval is not r. The maximal interval of existence is not the whole real number because the solution breaks down at x equal to 1 by a, which is a part of the real number. So the maximal interval will not be whole r. So C is not correct option. So this option 3 is not correct. So let's talk about option number 4. So option number 4, if f is bounded and continuously differentiable on R, then f is globally Lipschitz function. Therefore, the solution will exist globally. That is, the maximum interval of existence is R. So the fourth option will be correct. So when will be the maximal interval of existence equal to the whole real line? When f is bounded and continuously differentiable. So the option 4 is correct. In conclusion, the option 2 and 4 are correct option, 1 and 3 are incorrect option. This problem is from CSIR NET June 2016 problem. So the problem is for lambda belongs to R. Consider the differential equation y dash x equal to lambda sine x plus y, where y0 equal to 1. Then this initial value problem has first option, no solution in any neighborhood of 0, a solution in R if lambda mod lambda less than 1, a solution in a neighborhood of 0, a solution in R only if mod lambda greater than 1. So if we compare it with y dash equal to f of xy, then f of xy is lambda sine x plus y. Since it is a trigonometric function, it is continuous everywhere. Now mod del f upon del y, we will partially differentiate f with respect to y, then we will get lambda. The derivative of sine is cos x plus y, which is less than equal to mod lambda for all lambda. The bound does not depend on x or y, so it is globally Lipschitz continuous function with respect to y. Therefore, by Picard-Lindelof's theorem, the solution of the initial value problem dy by dx equal to f of xy, y0 equal to 1 has a unique solution in R, that is on the whole real line. Now we will examine the options. No solution is not correct, it has a unique solution. A solution in R if mod lambda. Indeed, this problem has a solution in R for all the values of lambda, so it is correct option. A solution in a neighborhood, it is also correct. A solution in R only if mod lambda greater than 1. This part is correct, but here it is written that only if. It is not true because the given initial value problem has solution for all lambda. Therefore, this option will be incorrect. Hence, option B and C are the correct options. Next problem is from CSIR NET June 2017. The problem is, if the solution to the initial value problem dy by dx equal to y square plus x square subject to the condition y0 equal to 2 where x is greater than 0 exists in the interval 0 to L0 and the maximal interval of existence for the initial value problem dz by dx equal to z square subject to the condition z0 equal to 1 where x is greater than 0 is 0 to L1, then which of the following statements are correct? So basically there are two initial value problem and their interval of existence are given. It's 0 to L0 and 0 to L1. So we have to find the value of L0 and L1. So let's do it. The first initial value problem is dy by dx equal to y square plus x square subject to the condition y0 equal to 2. We assume fxy as y square plus x square, which is a continuous function on the all real numbers. Now there is a comparison theorem for differential equations which states that if y dash x equal to fxy and u dash x equal to g of u with the condition that fxy greater than equal to gy and y0 equal to u0. If these are the conditions, then yx greater than equal to ux for all x in the common interval. So we will use this comparison theorem to find the value of L0 because by direct method we cannot find the value of L0. The domain D is not explicitly given. It is only given that x is greater than 0, that is it is unbounded domain, so we cannot make any conclusion based on the basis of this. So we will use this comparison theorem. It is very important theorem for this question. So we have fxy equal to x square plus y square, and for x greater than equal to 0, this is always greater than equal to y square. So we will consider the initial value problem in comparison theorem. We consider a secondary initial value problem u dash x equal to g of u. So we will condition, we will use u dash and du by dx equal to u square subject to the same condition because the condition on y is given as y0 equal to 2, so we will use the same condition u0 equal to 2. Then fxy, which is x square plus y square, will be greater than gy because we have considered g as u square, so gu is u square, so gy will be y square. Now we will solve the initial value problem du by dx equal to u square. So we will separate the variable on integration. It will give 1 on u with minus sign equal to x plus g. Since the initial condition is u0 equal to 2, the value of constant will be minus 1 by 2. So minus 1 upon u equal to x minus half, and the solution of the initial value problem u dash equal to g of u equal to u square subject to u0 equal to 2 will be 2 upon 1 minus 2x, where x is not equal to 1 by 2. When x tends to 1 by 2, the solution will tend to infinity. So the maximum interval for the initial value problem du by dx equal to u square, u0 equal to 2 is 0 to 1 by 2. And by comparison theorem, yx will be greater than equal to ux. But since ux tends to infinity as x tends to 1 by 2, it means yx cannot exist past x equal to 1 by 2. Therefore, L0 must be less than equal to 1 by 2. Now we will analyze the second initial value problem dz by dx equal to z square subject to z0 equal to 1. By using the method of separation of variables, the solution will be z equal to 1 upon 1 minus x. when x not equal to 1. So the maximal interval of existence will be 0 to 1. Therefore L1 equal to 1. So by analyzing both the initial value problems, we got L1, L0 less than equal to 1 by 2 and L1 equal to 1. Now we will check each options. In first option, L1 equal to 1 is correct, but L0 is less than 1 by 2, not greater than 1. So this option is not correct. Second option is correct because L1 is 1, okay, but L0 is less than equal to 1 by 2 is also less than equal to 1, because so option B is correct. Option D, L1 equal to 1, which is also less than 2, so it is also correct option. And the last option is L1 greater than 2, which is not correct because L1 is 1, which is not greater than 2. So option 2 and 3 are the correct option for this problem. So this is it for all. In next lecture, we will discuss some other problems on differential equations or initial value problem. Till then, keep learning, keep exploring, and thank you for watching.